Electron Configuration Part 1. Electron configuration is a means by which we look at the distribution of electrons within an atom and determine the relative energies, energetics of these electrons, as well as their locations, probabilities, things of this nature. All atoms will seek the lowest possible energy configuration that they can achieve. In order to do so, electrons are placed into orbitals in such a way as to minimize energy. All atoms which have more than one electron will have different orbitals, and each of the orbitals will have different energies. There are three principles which govern the configuration of electrons in an atom. The Aufbau principle states that electrons will occupy the lowest energy orbitals first, which means that they will not occupy higher energy orbitals until lower energy orbitals are filled. Hund's rule says that electrons will occupy degenerate orbitals, that is, orbitals which have the same energy, one electron at a time before they begin to put two electrons in the same orbital. The Pauli exclusion principle states that no two electrons in the same atom will have the same four quantum numbers. If you recall before, we did the four different quantum numbers that were predicted by the Schrödinger equation: the n value, the l value, the m sub l value, and the m sub s value. The Aufbau principle, upon closer examination, once again, is that electrons occupy lowest energy orbitals first. The orbitals within an electron are named based upon their subshell. The L value determines the particular name of the subshell. The value of 0 is called an S subshell. The value of 1 is a P subshell. 2 is a D subshell. 3 is an F subshell, so on. The first four are S, P, D, and F. From there, the orbitals go in, or the subshells go in alphabetical order: G, H, I, J, K, whatever. From that point, no electrons exist in currently known elements that occupy beyond the F subshell in their ground state or lowest electron configuration. So the F subshell is the last one of which we are particularly concerned. The higher the N value of an electron and the higher the L value of an electron subshell, the higher the overall energy. So a 1s subshell, which has an N value of 1, will be of lower energy than a 2s subshell. At the same time, a 2p subshell will be of higher energy than a 2s subshell. So the higher the L value relative in the same N value, the higher the energy. The higher the N value overall, the higher the energy. As we stated, within the same N value, the higher the L value, the higher the energy overall. However, we can have some L values that exist with lower N values that have higher energy than values of L that are in higher N values. For instance, the 3D subshell is actually higher energy than the 4s subshell. Because electrons will always fill the lowest energy orbitals first, they are not necessarily going to fill the lowest N value first. There is a diagram that we can look at to determine the order by which electrons fill orbitals, generally speaking. Looking at this diagram, in order to determine how the orbitals are filled, we go from the first arrow top to bottom that we encounter, start at the tail of the arrow and work towards the head. Every orbital that is crossed is filled in the order that it is crossed. So starting with the first arrow, we cross a 1s orbital, and that is all. Move then to the second arrow, which crosses a 2s orbital, and that is all. The third arrow is the first one in which we cross over more than one orbital, starting with a 2p and then a 3s. So as we move down, we see that we cross across 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s. So we see here an instance in which as we said, the 3d orbital is actually higher energy than the 4s orbital. So we fill the 4s before we fill the 3d. We have the same phenomenon with the 4d orbital, which is filled after the 5s orbital, and so on and so forth. There are some exceptions to the filling diagram that we look at. For instance, some of the higher in-order L values are much closer in energy to each other. For example, the D's and the F's are closer in energy than the D's and the P's are. Energy overall can decrease when an orbital is occupied. And so until orbitals are actually occupied, sometimes orbitals are actually somewhat fluctuating in their energy level, which can cause what would normally we would assume to be an orbital filled first to be one that is filled later on. If I look at some particular orbitals, I begin to fill orbitals until they are either full or half full, and then I will actually switch to other orbitals later on. Looking at lanthanum, for instance, we would expect lanthanum, based on its position in the periodic table, to fill the 4f orbital before it filled the 5d orbital. However, it actually fills the 5d orbital first before filling the 4f. The next element in the periodic table begins to fill the 4f, and then as I proceed across the 4f, I'll actually eventually take that 5d out, and there'll be no more d's going across the lanthanide series until I get to the end of the particular series. Now, Hund's rule states that electrons will occupy degenerate or equal energy orbitals one at a time before they begin to pair. This is due to the fact that electrons repel each other because of their charges, both being negative charged particles. If I put two electrons in the same orbital, it increases the overall energy of that orbital because of the electron repulsion that is going on. So in order to avoid this high energy from repulsion, we fill the orbitals one at a time, so long as the orbitals that we're filling have the same energy. If I have, for instance, a p subshell, which has an L value of 1, the p subshell has m sub L values of -1, 0, and 1, which means that that p subshell has 3 different orbitals that are all of the same energy. The 3 m sub L values mean 3 orbitals, and all being the same energy, I fill one at a time before I begin to pair. So if I look at the order of filling, I fill all 3 with a single electron, rather than filling the first one with 2 electrons and then moving on, like you would expect, just filling up along the order. The Pauli exclusion principle, as the last principle we discussed, talks about how no 2 electrons in an atom can have the same 4 quantum numbers. This is where we get our limitation of 2 electrons per orbital. The Pauli exclusion principle introduced the value of m sub s, or the spin value. Because the m sub s values can exist only as positive or negative 1/2, each orbital can hold only 2 electrons. If an orbital, for instance, has an n value of 2, an L value of 1, and m sub value of -1, then one electron in that orbital can be plus 1/2, and the other one can be minus 1/2. I cannot have an instance where I have 2 electrons that are plus 1/2 or 2 electrons that are minus 1/2. For each subshell, then, the total number of electrons is equal to the number of orbitals times 2. So looking at a diagram of that, our s orbital or s subshell rather, with 1 orbital can have 2 electrons. The p subshell with 3 orbitals can have 6. The d with 5 can have 10, so on and so forth. The number of orbitals increases by 2 with each subsequent value of L, which means that for each increasing level of my subshells, my number of electrons will go up by 4, 2, 6, 10, 14, 18, so on.